if we start talking about temperature as how hot or cold something is, like, that's true, but it's also true that there's a lot more information behind that temperature, right? It has to do with how much pressure is in your system, how quickly are the molecules moving, how concentrated are the molecules, right? Are they running into each other a lot? Are they really, really high energy? Are they low energy? Things like that. If you've got molecules that have a higher velocity and that have a higher energy, internal energy, do you think you've got a hotter system or a colder system? Hot, right? The more those molecules move and interact and combine with each other, that raises the pressure, and that has fluctuations with temperature. And so you've got to think about the bigger picture relationship that goes with temperature. It's not just how hot or cold it is. It really has to do with the movement in those molecules and the energy that's conserved within those molecules. So 3 different ways we can measure temperature. Celsius and Fahrenheit are common, right? Fahrenheit's not probably as common for you guys, right? You measure everything with Celsius. Agreed? Have you dealt with Kelvin before? Yeah? Okay, Kelvin is truly the scientific unit for temperature. Celsius is the secondary because it's used by everyone else in the world except America. But in science, you only deal in Celsius or Kelvin. The good thing about Celsius and Kelvin is that it's a completely easy conversion. It's just an addition, right? So if you've got a Celsius temperature, all you do is add 273 to get that into Kelvin. Okay, so if your temperature was freezing, which in Celsius is what? Right? If I have something that's freezing, I'm sorry, I guess I should have said water. If water was freezing, that's 0 Celsius. So that means water freezes at 273 Kelvin, right? Do you know what the point is that is called when Kelvin equals negative 273? I'm sorry, no. I said that backwards. What is it called when Kelvin is equal to 0? Do you know what that's called? This would mean that Celsius is equal to negative 273 degrees Celsius. Do you know what that's called? That's right. That would be a point in which molecules cease to move, which would be the end of existence, right? That would not be good for us. Okay, that's called absolute zero. That's what that's called. When Kelvin reaches 0, that's called a point which is called absolute zero. Okay, and so that just means molecules don't have the energy to even vibrate, right? They just stop moving altogether. So, all right, let's go ahead and move into something called thermal equilibrium. Do you know what equilibrium means? Equilibrium means that just 2 things are now equal, right? It's very simple. Equilibrium just means 2 things are equal. So here's what thermal equilibrium says. When 2 objects are placed in thermal contact, heat is transferred between them. They eventually reach equilibrium, which is when both objects are at the same temperature now. Okay, and at this point, our heat transfer stops. Okay, we see this concept happen all the time in real life. An easy kind of way for us to think about thermal equilibrium is if you put an ice cube into a cup of water, right? Eventually that ice cube does what? It melts, right? Because the water itself was a warmer temperature than the ice cube, and so it will melt. And so now you've just got cold water. And then after, 30 minutes to an hour, that water is not even cold anymore. Because what temperature has it kind of soaked up or adapted to? The temperature of its surroundings, right? The room temperature. And so it really happens twice in a very, very common scenario, right? Once the ice cube gets placed in the water's transferring heat to that cube and melting it down until it all becomes, roughly 1 degree Celsius, right? It's slightly above freezing. It's really cold water. And then after it sits at room temperature for a little bit, the heat from the surroundings will be flowing through that water, or that cold water will be pulling in the heat from the surroundings, and then it'll eventually reach room temperature. And so that thermal equilibrium happens twice. this is actually called the 0th law of thermodynamics. Okay? Like they came up with the first, second, third law, and then they decided to go back and add this obvious one, and so they called it the 0th. Okay? Okay, so here is another kind of way of saying this. If there are two systems in thermal equilibrium with a third system, then they're in thermal equilibrium with each other. Okay, this is kind of another way of rephrasing what we said, right? They're eventually going to reach this thermal equilibrium. If you have two things that are in thermal equilibrium with each other, if two systems are in thermal equilibrium with a third, then that means they have to be in thermal equilibrium with each other. So if A is in thermal equilibrium with C and B is in thermal equilibrium with C, then A and B has to be in thermal equilibrium with each other. There's a math law that goes with that too. I don't know what it is. Okay, but it's the same thing. Okay, so this, I guess I shouldn't have said 0th law up above. It really fits with this A equals C, B equals C, so A equals B. Okay. The reason we're talking about thermal equilibrium and temperature and everything like that is that we're going to start looking at something called thermal expansion. Thermal expansion. Thermal expansion happens when things get really hot or really cold, and the molecules themselves either spread apart or shrink up. Okay, when do you think we would see molecules start expanding in size? When it's hot or when it's cold? When it's hot, right? So when we start looking at thermal expansion, you're going to start noticing it in your everyday life. Okay, I want you to think about just like your hands. When your hands get really hot and they get you've been using them a lot, or they're like sweaty, what happens to your fingers? Have you ever noticed that your fingers kind of swell up when you get hot? Right? If you wear jewelry or if you have something on your finger and you can't get it off all of a sudden, what do they tell you to do? If you put it in ice water, your fingers will stop swelling. They'll cool back down, right? They'll become smaller and you'll be able to get your jewelry off, right? That's an easy example of thermal expansion. It also happens a lot with roads and sidewalks and construction like that. Sometimes you'll see like rubber seams that are built into roads, and that's so in the summer when it gets hot, those concrete slabs can expand and squish that rubber and not crack, right? If it was all just one solid piece of concrete and it was expanding, the roads would crack during the summer. They would get all broken up. It would be a kind of a mess. So those things are even taken into account in big picture projects. So here's thermal expansion. We're going to start looking first at thermal expansion in terms of length. How do things get longer or shorter when they heat up or when they cool down? Okay? The amount to which a material expands or contracts with the heat deals on the material itself. And so that's why I gave you that sheet that she passed out. It's got some constants for us that are material dependent. And so there's a much bigger... you'll see some materials really expand very easily and some materials don't. Okay, and so we're going to look at what those coefficients mean here in just a little bit. But this will be a value that this table will include values that you'll need to help solve the problems. Okay, so here is our equation for thermal expansion. The change in length of the material is proportional to the change in temperature. And so delta always means what? It always means change in, or it means final minus initial. So this would be length, right? The final length minus the initial, or how much longer it got, is proportional to A. This is called the coefficient of thermal expansion. I didn't spell that right. Sorry. Coefficient of thermal expansion. And it's an A or an alpha right? It's really an alpha character, so kind of like that. That alpha character or this alpha coefficient is when it is linear. Okay, when we start looking at volumetric expansion, you're going to see it use that B or that beta. Okay, so alpha is when we're talking about linear expansion, and B or beta is going to be when we talk about volumetric expansion. Okay? All right, then L sub O, what do you think that stands for? What'd you say? Original length. Good, original length. The O just means like at time 0, that's all it's saying. And so we're talking about the original length, and this is going to be change in temperature. If you notice, the coefficients on your sheet are measured in per degrees Celsius. That is their unit. And so that means your change in temperatures need to be in Celsius, right? Or Kelvin, because the change in Celsius and change in Kelvin would be the same. Okay, but they cannot be measured in Fahrenheit. So if it is Fahrenheit, you have to use that conversion we gave you at the beginning to put those into Celsius. Okay. All right, so I gave you those coefficient values. The common ones that we're going to use would be steel. Okay, or it's called stainless steel here. That's going to be a common one that we use. Water, a little bit when we get to volume. But this was the best table I could find real quickly. If we need other ones, we'll be able to just look them up as we go if we need coefficients of other values. In my other textbook, they had a big table in the textbook, but your textbook does not have that. So I just found one real quick for you this morning. Okay. The steel bed of a bridge is 200 meters long at 20 degrees Celsius. If it's exposed from temperatures from -30 to +40, how much will it expand and contract? Okay. Question. In this question, it's asking us for two different things. How much will it expand and how much will it contract? Which means we're not going to be able to solve this in just one equation. We're going to have to look for the value of its length after an expansion and the value of its length after a shrinking, right? Okay, or after it shrinks. So if I'm going to do this, I'm going to look at my equation again, right? My equation is change in length equals alpha times length original times delta t. And so really, I don't really need to find its final length. I just need to go ahead and find the change in, right? I know my original length is 200. I know my coefficient here based on my sheet is going to be steel. So that's 17 times 10 to the -6, right? Because we see it's times 10 to the -6 up here at the top. Times my original length, bless you, times my change in temperature. And so do we want to look first for the expansion or for the contraction? Expansion. So if I'm looking for expansion, should I pick the hot temperature or the cold temperature? Right? If it's expanding, is the temperature warming up or cooling down? Warming up. So I need to go ahead and go 40 degrees minus 20 degrees. Right? Because this is the hot temperature. It starts at 20 degrees. Right? At our normal length, it's 20 degrees. And so I'm looking at from normal to warming up to 40, how much is it going to expand? Right? I don't need to know how much it's going to expand from its coldest to its hottest. We want to know from normal, what is its expansion value. So now we can go ahead and solve. Okay, go ahead and grab your calculator out, please. So I got 0.068 meters. Okay, I want to change our coefficient here for regular steel, not stainless steel like our table says. Should be 12 times 10 to the -6. And so if I run the math again with that, I'm going to get a little different value here. because the table I gave you only had stainless steel, but I want the value for just steel, so I had to look that up. Okay, and so I got 0.048 meters. What'd you say? Oh, I'm sorry. All right, so the second part of our question wants to know how much now will it contract? So I'm looking for my change in length. It's still steel, so we still keep our steel coefficient. Our original length was still 200. Our final volume is -30 minus 20. Okay, if we look at this value here, we didn't see a super change in temperature. This is going to be a much more drastic change in temperature because we're moving 50 degrees away instead of 20 degrees away. So we should see a bigger value for our contraction here. Okay, so if I run the math on that, 12 times 10 to the -6 times 200 times -50, our value is going to come out negative 0.12 meters. And so the negative just tells us that it's doing what? Yeah, it's just telling us that it's getting smaller, right? Our length is getting smaller. That's all it's telling us. An iron ring needs to fit snugly on a cylindrical iron rod. At 20 degrees, the diameter of the rod is 6.445 centimeters. The inside diameter of the ring is 6.420. To slip onto the rod, the ring must be 0.008 centimeters larger. Excuse me. To what temperature does the ring need to be to fit? We first kind of need to figure out, well, what do we need for our ring to be, right? If it says the diameter of the ring is this, the diameter of the rod is this, the ring is this, but it needs to be 0.008 centimeters larger than the rod. Okay, so that means we need the ring to be a total of, let's see, 6.445 plus 0.008. We need the ring to be 6.453 centimeters across. Agreed? Okay, and so essentially what I've got to do is I've got to find my change in temperature, okay, because it's at 20 right now. It says, to what temperatures does the ring need to be heated? I don't know why I left that out. What does it need to be heated to be able to fit? Okay, so here's what I need it to be. This is what I need my ring to be. Currently, my ring is only at 6.420. So that means my change in length, or the change in diameter, would be 6.453 minus 6.420. That would be like my change in length, right? Here's my original. Here's what I need it to be. Equals, it's a, what kind of ring? An iron ring. Do you guys have iron on there? Oh, goodness, you don't. Okay. The iron, it's the same as steel. 12 times 10 to the -6. Okay. So my alpha coefficient is 12 times 10 to the -6. My original length was 6.420. And then my change in temperature, you could go ahead and say TF minus 20 if you want, or you could just solve for delta T and then subtract 20 later. It doesn't really make a difference what you do. I'm going to go ahead and leave it set up like this. So my change in length over on the left, 6.453 minus 6.42, gives me 0.033 equals. And then my right side times 6.420. So that gives me 7.704 times 10 to the -5th times TF minus 0.001541. So I'll add that to the other side. that gives me 0.034541 equals 7.74 times 10 to the negative 5th TF. So divide that over. And so that gives me a final temperature value of 446.3 degrees Celsius. So that's what temperature it needs to be heated to in order to expand enough to fit over that system. Okay, does that kind of make sense how we worked that out? We were given an original diameter. We were given what we need, right? It's got to be so much bigger. We solved for the change in that and then solved for our final temperature. So volumetric thermal expansion is the change in volume of a material which undergoes a temperature change, and we find it using an equation that looks extremely similar to our length one, right? Only it's now change in volume equals beta times our initial volume times change in time. Okay, so the equation looks extremely similar, except now beta is the coefficient of volumetric expansion. Those are on your table as well. It looks like I'm going to have to add a couple values to your table here for our next problem, but I'll give you that when we need it. B is a beta value, and that's your coefficients for volume. Yep, it's a volumetric coefficient. Okay, this says a 70-liter steel gas tank of a car is filled to the top at 20 degrees Celsius. The car sits and reaches a temperature of 40. How much gas would overflow from the tank? Okay, so let's look at a couple different things here. We've got to take into account two different issues, right? We're going to have expansion of both the tank and expansion of the gasoline. Agreed, right? They're both going to have some expansion here. And so we're going to look at how much they're each going to expand to see, is the gas tank going to expand enough to withhold that gas, or is the gas going to expand enough to spill out? Okay. So let's have our first portion of this problem examining just how much the gas itself is going to expand. Okay, so you're going to have to add gasoline to your thermal expansion coefficient values. And so the beta value, let's just give you the beta values for gasoline. Gasoline, what you put in your car. The beta value for that is 950 times 10 to the negative 6th. Okay, so beta value for gasoline equals 950 times 10 to the negative 6. You don't need the linear coefficient for gasoline because you don't. You won't have solid gasoline that's getting longer. Okay, so let's start thinking about this. Our original volume of gasoline, right? If I'm trying to find out what's my change in volume going to be, my beta value is 950 times 10 to the negative 6th. My original volume is going to be that full 70 liters, right? It's got to be my full 70 liters because it says my tank is full. And then the car temperature goes from 20 to 40. So I'm going to take final minus initial and see what's my change in volume here. Okay, so my change in volume equals, I got 1.33 liters. Okay, 1.33 liters. So in all reality, that's a pretty good, that's almost 2% overflow, right? That's a pretty big quantity in terms of your gas in your car, right? You don't want to lose that much gas after you just filled it up, right? Okay, second part of it now, if we are looking at the tank itself, my change in volume of my tank, it says it's steel, so we're going to use our beta coefficient for steel, which is 35 times 10 to the negative 6th. It started out at 70 liters, and it's going to have the same temperature change. Okay, so that's 35 times 10 to the negative 6 times 70 times 20. That means my tank only expands 0.049 liters. Okay, and so if I'm really losing 1.33 liters, but my tank grew by that many, 1.33 minus 0.049 would give me a total loss in gas of 1.281 liters. All right, does that make sense? My tank got a little bit bigger, so it allowed me to have a little bit more gas in there, but then I still didn't have enough room. All right, so my total loss or my overflow of gas would have been 1.281 liters.